In a previous video, we established the bipositional switch, which we called as the switching power pole, as the building block of most of the voltage source converters. In this video, we will discuss the power pole in more detail and derive an average model for the power pole. The average modeling is important because in power converters, almost all the control objectives are achieved essentially by controlling the average value of different quantities. So we need to come up with a formal definition of averaging. So what we use is the cycle by cycle averaging, or CCA, which essentially is the average of a quantity over a complete switching period. We denote the cycle by cycle average value of quantities by a bar on top. So for example, VAN with a bar on top denotes the cycle by cycle average of this instantaneous pole output voltage. Similarly, ID with a bar on top represents the DC current, its average value. So this is the formal mathematical expression for the cycle by cycle average. So the CCA of a time varying quantity x of t is denoted by the bar on top x bar of t, and is defined as integrate this x of t over one complete switching period, starting from t minus ts, where ts is the switching period, up to t, and then divide by ts to get the average over one switching period. So pictorially, let's say this blue waveform is the x of t. It could be a voltage or a current or any other quantity. And if you're interested in finding its CCA value at say exactly at this time, denoted by this red point, then consider one switching period before this point, before time t. So that will be this shaded box. So just take the average of this blue waveform in that box. That gives us the CCA value at this instant. So in this plot, the red line indicates the x bar of t, the average CCA average of this instantaneous x of t, and so the average x bar of t happens to be a constant because the average of this blue over one complete period is exactly constant at every point in time. So when we develop the average models and do the controller design using these average models, we are essentially dealing with the cycle by cycle averaged quantities. And another important point to note is that even though it is an average, the cycle by cycle average quantities can actually be time varying. And in the case of DC to DC converters, they are time varying during transients. And in the case of DC to AC converters, that is what our focus is on in this module, even in steady state, the CCA quantities are time varying. Okay, then a list of some properties of CCA quantities that will be very useful in our analysis. So I'm comparing the instantaneous relationships and the cycle by cycle average relationships. For a resistor, obviously Ohm's law V of t is R times I of t. That is equally valid in an average sense as well. So average voltage is R times the average current. And for an inductor, the current voltage relationship is instantaneously VL of t is L dI over dt. And the same relationship is true in an average sense as well. So the average voltage is L times the derivative of the average inductor current. So it's dual, which is for the capacitor, IC equals C dV over dt. That is true both in an instantaneous sense as well as in an CCA average sense. So we know that the sum of the currents entering the node in an instantaneous sense is 0. That is the Kirchhoff's current law. KCL is also equally valid for average currents as well. The sum of all the average currents entering a node at a given time adds up to 0. Similarly, KVL is true both in an instantaneous as well as in an average sense. The sum of the voltage rise or drop going around the loop in an average sense also adds up to 0. In the process of deriving the cycle by cycle average quantity, we essentially remove the switching frequency and its harmonics in that quantity, retaining only the DC and the low frequency fundamental frequency AC component. So therefore the CCA quantities can be used in a phasor analysis, which requires that there is only one frequency, and in this case that will be the fundamental frequency. For the same reason, since the CCA removes the switching frequency related information, it can only be used for fundamental frequency analysis or a DC analysis, and it cannot be used to study, for example, the switch stress or the switching frequency ripple in any quantity. Now coming back to the power pole shown here, let's derive the CCA value for this pole output voltage marked as VAN, the pole A voltage with respect to the DC negative. So here is the waveform of VAN. It is equal to VD whenever Q is 1 or the top switch is on, and it is 0 when Q is 0. So in one complete switching period, the VAN equals VD for a duration of T on, and it is 0 for the remaining duration. So let's apply the definition of CCA to this VAN. So it will be the integral of VAN over one complete switching period divided by Ts. So we see that in any switching period, VAN has a value of VD for exactly T on seconds, and it is 0 for the rest of the period. Therefore the average is simply VD times T on over Ts, and we note that T on over Ts is the instantaneous duty ratio D of T. Therefore the derivation is that the cycle by cycle average value of the pole output voltage is simply the duty ratio D times the DC voltage, the DC link voltage. So now we can use this relationship and our earlier derivation of the relationship between D and the feedback controller's output, the control voltage VCA, to show that the power pole is really a voltage amplifier. Okay. So this is what we derived, the relationship between D and VCA. D of T instantaneously is 1/2 plus 1/2 of the control voltage. And just in the previous slide, we saw that the average pole output voltage VAN bar is the VD times D of T. So putting these two together, we see that the pole output voltage in an average sense is VD over 2 plus VD over 2 times this VCA of T, the controller's output voltage. So therefore we see that the power pole is the switching power pole in an average sense is essentially an voltage amplifier. It amplifies the control signal by a gain of VD over 2, and it also adds a DC offset. So there is nothing unique about sinusoidal signals. In fact, the power pole can amplify any arbitrary voltage wave shape. The only limitation for this analysis is that the frequency in that waveform has to be well below the switching frequency for the averaging process to be valid. And also note that this CCA averaging is valid for both steady state as well as transient analysis. Okay, let's do a quick example. Here is a single power pole converter, and I give the control voltage to be this expression. So it has a 50 Hertz component, 0.7 volts amplitude, and it has a 150 Hertz component at 0.2 amplitude. So that's the control signal, and you can see that the VCA is between -1 and 1, which is a requirement. And the problem is to calculate the average of the pole output voltage given this control signal, and using simulation get the plots of the instantaneous and the average VAN, and also obtain the frequency spectrum in both of these instantaneous and average VAN. So it's straightforward. We just derive what is VAN average. It is this expression VD over 2 plus the same VD over 2 is the gain of this VCA. And VCA is known. Therefore, it's 100 volts DC voltage if you looked at the previous slide. So the DC offset is 50 volts, and the signal is amplified by a factor of 50. So the 50 Hz component is 35 and the 150 Hz component is 10. So this would be the this is the control voltage applied in simulation, and this is the switching signal, the green waveform. That is the instantaneous VAN. And as expected, it is switching between 100 and 0, and its cycle by cycle average is what is shown as this red waveform, and that follows this control signal waveform but amplified by a gain of 50. and it also has a DC offset added. So you can see that this waveform is symmetric, not with respect to 0, but it's symmetric with respect to the 50 volts point, which is the DC offset. And the AC component is just the same as the control signal times control signal with a gain of 50. And also note that I'm using a switching frequency of 10 kilohertz in this simulation. So here is the frequency spectrum of both of these instantaneous and average VAN. The green waveform is the FFT of VAN instantaneous, and the red is the FFT of VAN average. So if you zoom in near the low frequency region, you can see that both of these waveforms have large DC offset, 50 volts, 100 volts over 2, as expected. Both of them have a large 50 Hz component, that is 0.7 times 50 or 35 volts, and they also have 10 volts component at 150 Hz. They were as expected. If you zoom in near the switching frequency range, which is as I said 10 kilohertz, it's a 10 kilohertz point, you can see only the green, which is the instantaneous VAN, has this switching frequency component and its sidebands. It also has harmonics near 20 kilohertz and beyond in the green waveform and not in the red waveform. So the high frequency content and its the switching frequency content and its harmonics have been eliminated in the process of averaging. So with this, we are now ready to start deriving the complete average model of a power pole. So here is the power pole, and we defined this as a two-port network. The voltage port across the two end positions and a current port between this point N and the pole output A. So it's three terminals because one terminal is common to both the voltage port and the current port. So the derivation of the average model simply requires calculating the relationship between the two voltages and the two currents of the two-port network. So in this slide, we look at the voltage equation. So again, in an average sense, the voltage port voltage, which is VVP, VP suffix stands for voltage port, that is required to be a constant DC. Therefore, it's instantaneous as well as the average value is simply VD. So VVP is VD. The other port voltage, the current port voltage, which is VCP, CP stands for current port. So that is this waveform. So it is VD when Q is 1 and it is 0 when Q is 0. And we already derived its average. This is simply VAN. We derived earlier that it is VD times D of T. Okay. So the one of the two equations to derive the complete model that we are looking for is the voltage equation, which says the VCP average is D times VVP average. Next, we will look at the current relationships. So in almost all power converters, the pole current, which is typically an inductor current, has a piecewise linear waveform as shown by this red waveform in the middle. So it rises during the T on interval and it falls during the off interval. So this is the pole current. It is also the same as the current port current flowing here. So if you look at the voltage port current IVP, that is defined as IDA, that refers to the DC current due to pole A. So that during the on interval is exactly same as the current port current. So the voltage port current here during the T on interval is exactly same as this. And during the remaining interval in the same switching period, it is exactly equal to 0. I define the value of the inductor current at the start of the cycle as I1, its value at the its peak value, which happens at the end of the on interval, as I2, and its value at the end of complete period or at the beginning of the next cycle as I3. Now in DC-DC converters in steady state, I1 equals I3. During transients or in DC-AC converters, it is not exactly equal. But in this slide, let's just consider the case where I1 equals I3, meaning the current waveform starts and ends after one period exactly at the same value. So that is IA of t is equal to IA at t plus ts. So in that case, the IVP average is is the average of this waveform. That would be the area of this trapezoid, I1 plus I2 over 2 times T on divided by Ts is its average. T on over Ts is dA. So this is the average value of IVP or IVP bar. For the inductor current, the current port current, the average is simply I1 plus I2 over 2 because I1 equals I3. So putting these two together, we get the IVP bar in terms of the ICP bar as IVP bar is D times ICP bar. Okay, that's the second equation that we needed to get the complete average model. Now, if we do consider the more general case where I3 is not exactly equal to the starting value I1, but let's say it is more than I1 by a very small amount epsilon. Okay. So in that case, the IVP average does not change because it does not see this epsilon increase in the off interval. So its average value is still the same as before. Whereas ICP average, the current port current average, has this extra term compared to the previous case. So the error we get in equating IVP bar to be D times ICP is shown here. So IVP minus dA times this quantity is this expression, and here the maximum value of D times 1 minus D is when D is 0.5, or so this D times 1 minus D is 0.25. That divided by 2 gives you the error to be 0.125 times the epsilon. Okay. So now epsilon is a very small value as long as you ensure that the highest frequency of interest, for example the frequency of the modulating waveform, as long as that is well below the switching frequency, then epsilon is a very small number. So in other words, this represents a sinusoidal rise. So if the main sinusoidal waveform is rising at say 50 Hertz, so at a switching frequency level which is in the 50 microsecond, 100 microsecond range, then the increase in I3 or the I3 minus I1, which is epsilon, is very small. So once again we are justified in expressing the IVP average as D times ICP average, provided of course the switching frequency is well above the modulating frequency. And so with this understanding, this expression is valid both in steady state as well as in transient, both for DC-DC as well as DC-to-AC converters. So this picture on the right shows the power pole as a two-port device. On the left side is the voltage port, right side is the current port. They share this common terminal. So the voltage and currents here are the VVP and IVP, and the voltage and the currents here are the VCP and ICP. And we just derived an expression relating the voltages and the currents in terms of the duty ratio D of T. Okay, so this is what we derived. VCP, the secondary side or the current port voltage is D times the voltage port voltage, and the voltage port current is D times the current port current. So this set of two equations look very similar to that of the equations governing a transformer. So in a transformer as shown here, this is the primary, this is secondary. The turns ratio is N as defined here. Then the secondary voltage V secondary is N times V primary, and the I primary is N times I secondary. So for example, if we consider the voltage port side as the primary, the current port side as the secondary, then we can denote the power pole in an average sense as an ideal transformer with a turns ratio of this instantaneous duty ratio. Okay, so this slide shows the complete average model of the power pole, which is nothing but an ideal transformer. But note that all the quantities here are average quantities. The voltage port voltage and the current port voltage and the current, they are all average quantities. And this D is inherently an average quantity. The D is actually the cycle by cycle average of the switching signal Q of T. So all the 5 quantities here are average quantities, and these are the governing equations. And so we can apply everything that we know about ideal transformers in the analysis of the average power pole. You have a few things to be careful about. So this average transformer model is only a mathematical model that is helpful in many analysis and controller design. But you cannot buy a transformer and use that as a power converter. Okay? for several reasons. First of all, in a real transformer, you cannot apply DC voltage to any of the windings, whereas here clearly we see that on the voltage port side, on the primary here, we apply a DC voltage, which is VD. And also real transformers, the turns ratio once designed is fixed, whereas here what we need is an instantaneously varying duty ratio. But the ideal transformer model is very useful in many analyses. It is valid both in transients and steady state analysis, and it's very useful in deriving the transfer functions needed for, say, controller design. Okay, then in simulation we cannot actually use the ideal transformer that is available in most of the simulation tools. The reason is, as I mentioned before, what we need is an instantaneously variable duty ratio, whereas all the ideal transformer models have a fixed turns ratio. So to simulate this average models, we need to implement the power pole as a transformer using the this control voltage source, control current source model. So essentially, you write the equations of the transformer. It says the primary voltage or the secondary voltage is D times primary voltage, and the primary current is D times the secondary current. So we need to implement that by using these control sources. And the other thing to note is the duty ratio comes from the control voltage VC, so that the expression for D is 1/2 of VCA plus a DC offset of 0.5. A quick simulation example to verify the matching of the switching frequency model and the CCA average model. So I'm using the same single pole power converter using the similar control signal that we analyzed in an earlier example, and I want to compare the results from the switching model and the average model. So here is the Plex schematic of the single pole converter. So the top obviously is the switching model, and the bottom is the corresponding average model. And notice I've given the same DC voltage and the same LR load to this single pole converter. Just the bipositional switch has been replaced by its average model, the transformer model. So I define this as a control current source, which is the measured current port current, this average IA, times the duty ratio D. And the D itself is VCA plus 0.5 times VCA plus another 0.5. So this point is D. That multiplied by this average IA, which is the current port current, is this current source value, the current drawn from the DC source or the voltage port side. Similarly, the voltage applied on the current port side, the VCP, is the same D times the measured voltage port voltage, which is same as this VD of 100 volts. So that's the ideal transformer implemented using the control sources, and I'm just going to compare the waveform of the pole output voltage VAN, the inductor current IA, and the DC current IDA, both from the switching model and the average model in these three scopes. Okay, first let's look at the VAN waveform. Okay, so the green obviously is from the switching model and the red is from the average model, and you can clearly see that the average model predicts the VAN average very accurately. This is exactly what we did as the previous example. The DC offset plus the gain applied to the control signal. Okay, next we will look at the inductor current waveform, which is same as the current port current from both the switching and the average models. So again, once again, the green waveform is from the switching model, so you can see the high frequency ripple, and the red is from the average model, and you can see that very correctly captures the average of the switching model current waveform. So you can see it is right in the middle of the switching waveform, so that shows it's our average model is valid both both during the steady state as well as during this initial transient as well. The last waveform that you'll see is that of the input DC current, which is the voltage port current, again from both the switching model and the average model. So the red average model is the cycle by cycle average value of the switching current. So if you zoom in, you can see that the from the switching model you get this pulsating current drawn from the input source, and the red is its cycle by cycle average value. So the simulation results gives us good confidence in the accuracy of the average model, the ideal transformer model, for both steady state and transient analysis. So in later videos, when we have more complex converters with multiple power poles, we will rely on this average model to do the analysis for fundamental frequency analysis and the average analysis.